Hello, welcome to the Light and Sporty Guy channel. I'm Jim, and today we're going to talk about why this popular demonstration of Bernoulli's principle has pretty much nothing to do with Bernoulli's principle. So in order to do that, first we're going to talk about what is Bernoulli's principle or Bernoulli's equation really? What does it really mean? What's the physics behind it? And what are all the terms in the equation and what they mean? And once we understand Bernoulli's principle, we will know why the claim that when I blow over this piece of paper, the pressure in this jet of air coming out of my mouth is lower than the ambient pressure because it's moving faster, and that's what causes the paper to move up. Bogus, and we'll understand why. Then we'll talk about what really makes a paper lift up, and we'll even do some flow visualization using a small fountain pump in the bathtub with some other bits and pieces. Explain and demonstrate really what's happening, what the flow looks like, why the paper would lift up because of the flow. And if you want to do all this for a science fair project, I think it's not bad. We've got some physical demonstrations, we've got some theory, we've got math. You could expand on the math if you need to, depending on what level of science project you're trying to do. And we're approaching a very popular myth and showing the fallacy behind it. And let's say we're making the world a better place. So, if that sounds interesting, hang on and we'll see what we can do. Okay, here we have Bernoulli's equation on the screen. It's basically the pressure plus 1/2 the density, denoted by the Greek letter rho, 1/2 density times the velocity squared, plus, again, the density rho times g, the acceleration of gravity, times a height above a datum. Those terms are constant along a streamline, okay? But what does this mean in a physical sense? Well, if we look at the middle term first, that's 1/2 rho v squared. If you were to put m, mass, instead of the rho, density, in that term, you may be familiar with the equation for kinetic energy, 1/2 mass times the velocity. So if I were to take this hammer and throw it across the room, okay, you would have a kinetic energy equal to 1/2 times the mass of the hammer times the velocity squared, okay? The problem with fluids is that, you know, this is a nice discrete thing. You know, I can hold it. It's one size, one mass, one shape. Fluids like air or water, you know, what's the mass of fluid? Well, it depends on how big and what shape. And it's not convenient to use mass like it is for solid objects, so we tend to substitute density for mass. 1/2 density velocity squared is an expression of kinetic energy of a particle of fluid. The third term, rho gh, the density times acceleration of gravity times a height, well, that's just gravitational potential energy. So if I've got this hammer, as I raise it up, I'm applying a force over a distance, and I'm doing work on that hammer, and that work represents an increase in the gravitational potential energy, okay? Same thing if I take a chunk of air or fluid or water, move it up, okay? I've lifted that up against gravity. I've done work on that particle of water or air or whatever fluid, okay? Yeah, so I've increased its gravitational potential energy. You know, the first term is pressure. That may not seem like potential energy, okay? But think about, so if I take this spring, as I pull on it and stretch it, okay, I'm again applying a force across the distance. That's work, okay, by definition, our definition of mechanical work. And, you know, for your science fair, you can look it up and include this kind of stuff, definition on your display. But I'm doing work on the spring, and I'm storing energy in that spring, and that energy, once it's in the spring, can do work on my fingers, okay? It's a potential energy. Now pressure, if I have a chunk of air, okay, and I have a high pressure on one side and a low pressure on the other, that difference in pressure is, well, pressure is force per unit area, so if I multiply by the area of my thing, my ball of air, that is essentially a force. And as I move along a streamline, okay, and if the pressure is changing, I've moved this air chunk against a force, I've done work, okay, or work has been done on it, okay. And what all this means is it's essentially saying that we have kinetic energy, the 1/2 rho v squared, we have gravitational potential energy, the rho gh, and we have potential energy related to the pressure, okay, the p term, and when you add those together, they're a constant, okay, which means that the amount of energy, the sum of those three forms of energy, doesn't change if you don't add or subtract energy. That may seem kind of trivial, but it's key to understanding all this. You know, that Bernoulli's principle is conservation of energy on a bit of fluid as it travels along a streamline, okay? Nothing more, nothing less. Okay, now that we have kind of a crude, rough, mechanical, solid mechanic analogies to the terms in Bernoulli's equation, let's put the whole equation together so we can understand what we mean, okay? So I got the hammer, and if I were to raise this up, I'm increasing the gravitational potential energy. If I pull it down, it's losing gravitational potential energy, but it's, as I pull it down, we're adding energy, potential energy in the spring, right? And as I move it up and down by hand, energy is not conserved in the system because I'm adding and subtracting using my hand. But once I let go, okay, at the bottom of the stroke, the potential energy in the spring is at a maximum. The potential energy due to gravity is at a minimum. And when it stops, my kinetic energy is zero. But then as it goes up, right, I'm trading this potential energy in the spring for kinetic energy and also increasing gravitational potential energy. Up here, where it stops, the gravitational potential energy is at the max. Kinetic energy is zero because it comes to a stop, and the potential energy in the spring is at a minimum, okay? But when I let go of this, I'm not adding or subtracting energy. Energy is being conserved mostly. I mean, there's some air resistance and losses in that spring, but for for simplification's sake, this is Bernoulli's equation, right? Energy is being conserved in this system. It's just transferring back and forth between kinetic and potential energies, okay? And that's Bernoulli, okay, as a mechanical, rough mechanical analog. Now, here we have a simplified version of Bernoulli's principle as it's typically used in aerodynamics. When we're looking at flow over a car, an airplane, a baseball, whatever, the change in elevation of the fluid is pretty minimal, and air isn't very dense, so the amount of energy it takes to move this air up this far is negligible in the larger picture, so we typically leave that term off. In this situation, our terms are the static pressure and the velocity, and you can see from the equation, if the pressure goes down, the velocity has to go up to maintain that constant total pressure, right? We're trading pressure energy for kinetic energy. So that's where we get the idea that faster is lower pressure from this equation. But then the next question is this really Bernoulli's equation that I'm giving to you here? So let's pop up some actual references here. This first one is from Abbott and von Dönhoff, Theory of Wing Sections, 1959. Abbott and von Dönhoff worked for NACA, which is the predecessor to NASA, and most of the airfoils that you find on reasonably modern aircraft, up until the 80s and 90s at least, came out of the studies these guys did at NACA. And in their book they derive Bernoulli's equation, and you can see it right there. That's just what you saw on the previous slide. Pressure plus 1/2 rho v squared is they called it H is a constant of integration or the total pressure. And again, there's the assumptions. Incompressible fluid, constant density, steady motion, integrated along a path, a single streamline, and only where streamlines in unaccelerated flow where the effects of viscosity and compressibility are negligible. Kind of what I said, right? Another reference here, this is from Streeter's Fluid Mechanics, 1971. Now this is a broader fluid mechanics text, not just aerodynamics, so he includes the gravitational term. That's almost exactly the same equation I had, the difference being he divided through by the density, rho. Algebraically, they're the same. This is from Anderson's Fundamentals of Aerodynamics, 1984. Again, the same aerodynamic form of the Bernoulli's equation. And that brings up another thing to my mind. In the popular literature, you'll often find things where they'll say, like the pressure on top of a wing can't be explained by Newton's laws, you have to use Bernoulli's equation. Or, you know, Bernoulli gives you the lift on the top of a wing, Newton gives you the lift on the bottom of the wing as the molecules are bouncing off. And that's all nonsense. You know, the idea that somehow Newtonian mechanics and fluid mechanics are disconnected, you know, that they're different rules of physics, different laws of physics, and that's just not true. You saw our mechanical analogy for all the terms in Bernoulli's equation, okay? If you were to pull up the Navier-Stokes equations, they look real complicated, okay? Because there's divergence and curl and it's three-dimensional, and but the terms in that equation, each one of those terms, plus the continuity equation, which is just conservation of mass, each one of those terms is either representing a force and an acceleration, you know, and the density substituting for mass. And the Navier-Stokes equations are really Newton's second law applied to fluids. It's not something different. And here's a snippet from Fluid Mechanics, Streeter, 1971 again. You can see that the analysis stems from the application of the principles and laws, starting with Newton's laws of motion. Fluid mechanics are Newtonian classical mechanics, okay? So let's apply Bernoulli's equation, or Bernoulli's principle, to our blowing over a paper demonstration, okay? So here's Bernoulli's equation, and I've applied it to the air coming out in this jet, okay? And we know that inside your mouth the pressure is higher before you start blowing, right? And as you blow, we got this jet coming out here, and the jet is moving faster than it was in your mouth. So we know that the pressure in this jet is lower than the pressure in our mouth, right? For that equation to be constant, since the velocity out here is faster, the pressure has to be faster. So Bernoulli tells us that the pressure in this jet is lower than the pressure in your mouth, okay? And that's fine, okay? But if we look at the ambient air surrounding the jet, right, there's Bernoulli's equation applied to the ambient air, and the air around that jet, initially at least, is still, so the velocity term is zero, so our total pressure out here is just the ambient pressure, and we know that the total pressure in this jet is higher than the total pressure around it, okay? And so we can substitute our other terms into the inequality, and we get the pressure in the jet plus 1/2 rho v squared in the jet is greater than the ambient pressure. And that's as far as algebra will take us in Bernoulli, okay? All we know is the total pressures are different. Bernoulli is not telling us that the pressure in the jet is lower than the ambient pressure because it's moving, because those are different streamlines with different total pressures, and never the twain shall meet, okay? So the claim in our demonstration that it's this lower pressure in the jet causing the paper to rise is not supported by Bernoulli. That's the simple mathematical fact there. But that leaves us with a mystery, of course, that because the paper rises, right, that means there has to be a net force to raise this paper up against gravity, which means that the pressure on top has to be lower than the pressure on the bottom. So where does that come from? Let's talk about viscosity. In our discussion of Bernoulli, we talked about ideal fluids and no viscosity, but what does viscosity do in this picture? Because as convenient as it is to ignore viscosity sometimes, it's there. It's not real high. For air, the viscosity is very low, the density is low, but it's not zero. So what viscosity is it's the friction between, or shearing force between one layer of fluid and another that are moving at different speeds. So if I have a high-speed jet of air, the air near that jet tends to get dragged in through viscosity and start moving, and it transfers energy to air further away and further away. And so we're transferring energy out of our jet into the surrounding air, and we're dragging it along, okay? And this is a big factor in what causes this paper to rise. Now that we know that Bernoulli doesn't explain what's going on, let's explore the effects of viscosity on our jet of bad breath that we're blowing here, okay? So we have this jet of air that's blasting out, okay? And because of viscosity, the air in the vicinity of that jet, so a little bit of air there is going to tend to get drug along, and this air is going to get drug along, and that air, same thing top and bottom, okay? And as we pull air out of this area adjacent to our jet, so it tends to reduce the pressure in the vicinity of our jet. So what happens in the end is the air flows into that slightly lowered pressure, and I mean slightly. The amount of pressure involved here to lift a piece of paper is really, really small, and certainly nothing I can measure in my shop with the stuff I have. It's small, other than to put a piece of paper and show, oh, the piece of paper moved, and we can deduce that there's a lower pressure because of that. But the flow is going to come in and get entrained, and we end up with a flow pattern where the flow is just moving along like that, okay? And you can imagine a piece of paper caught in this inward flowing air. If it was on the bottom, it's going to get sucked up along with the flow. So if we draw our piece of paper, as I said, it's easy to imagine that getting pulled up with the flow. But the other thing is, with that paper, it is blocking the flow of air in from here, right? So air has to come in, along the paper and then scoot out and along here. So you actually end up with what I suspect is an even lower pressure when you put that piece of paper in the way in this area between the paper and the jet, okay? And that's, again, going to cause our paper to rise. But the other thing that lower pressure can do is it will tend to pull our jet towards a piece of paper, okay, curve it down, and then at some point the jet might actually attach or flow right along that surface at some point. And we've curved the flow of the jet, okay? So Newton tells us that took a force, took a force to pull it down, and equal and opposite, we have force pulling the paper up. And that is what causes the paper to rise, is the effects of viscosity and the flow pattern we create around that piece of paper and around the jet. So, again, do you believe me? Or, I'm just drawing pictures here. I could draw just about anything, right? So let's go use our flow visualization methods and see if this is what happens in real life. Okay, so here's my super duper high-tech flow visualization system. Hopefully the sound of the fan overhead isn't too loud. It comes on automatic with a light. There's not much I can do about it at the moment. I've got a pump here, just a little aquarium pump, and that runs over to this nozzle over here where the water squirts out. So And I also have a glue syringe full of red food dye. I'm going to inject some food dye into the pump inlet, and we should be able to see what this jet of water looks like as it comes out of our nozzle, which is firmly duct taped to the bottom of the tub. Okay, now that we've looked at what the flow from that jet looks like, let's look at the flow around it here. One thing about this food dye is it's kind of heavy and it sinks pretty quick, and so I've sucked in a little water. I'll suck in a little more. I just dribbled some and it sank. Mixed some water in here, so hopefully it doesn't just boom sink to the bottom. And I don't have to repeat this again. So I'm going to take this dye, there we go, and if I put it in the water near the jet, you can see there's flow from the needle. It's just getting pulled towards that jet and zooped away, right? That's working nicely. I like that. Let me zoom you in closer. Okay, we're a little more zoomertized, and I will try to give a steady stream here, or a pulsating stream, I guess. But you can see the motion of the fluid. The fluid near the jet is getting pulled in and sucked away, okay? So we have a net inward flow. And if there were a piece of paper here, that piece of paper would get pulled up as that flow moves up. But let's look at what happens when we have something more like a piece of paper in the stream and visualize that flow. Okay, continuing on, I have a piece of aluminum, since paper wouldn't work, you know, it's doing it in water. And I have the jet of water coming out of the pump. Couple tips if you want to do this for science fair. You know, I 3D printed the support for the hose there. No need to get that elaborate. You could hot melt some popsicle sticks. That'd be one thing. Two things, make it shallower, like, you know, that's probably plenty deep enough, because you spend a lot of time emptying and filling the tub. So the pump is running, and as you can imagine, there's the jet of water coming out, and that jet, you know, this aluminum is blocking the flow of water. It can't get through there, right? So one of two things can happen. One, you know, as we pull water away from the space between the jet and the aluminum, it can come back and then get carried away like that, right? Or the jet can bend and follow that surface. And if one of those things didn't happen, right, if we sucked all the water out of here, we'd end up with a hole in the water, and that's just not going to happen. So we know there's either some recirculation or we're curving the jet. So I'm going to put some red dye in the inlet of the pump, and let's see what we can see. And this is where a picture of the without the aluminum and with the aluminum, I think, would help a lot as a comparison in your science project. Just use still pictures. Oh yeah, look at that turn. So I've increased the angle at which this is setting, and I've let the water settle for a while so it shouldn't be moving too much. I'm going to put some dye in here and then turn on the pump, and hopefully we can see how the, don't touch the water, we'll see how the dye gets entrained and flows out, and maybe even see the curvature of the flow, so you can kind of get a picture of how the jet of water evacuates water between the jet and the obstacle, creating the low pressure zone here as it sucks everything out. That's the theory. Let's see how this demonstration goes in practice. Okay, so you can see it moving this way, and then it gets to the actual jet, and then it gets entrained, and you can see it getting sucked away, those little tendrils. And that's what creates the low pressure. I think we should have a better feel for the actual flow and why there's this low pressure here, because you're sucking the water out from between the jet and our obstruction, simulating our piece of paper. And yeah, that's got nothing to do with Bernoulli. Nothing at all. And it, you know, basically we're violating all the assumptions that make Bernoulli valid, because we're transferring energy from our jet to the surrounding water to make it move, and that is a distinctly non-Bernoullian behavior. Okay, so what can we conclude after all that? Okay, first of all, we know that Bernoulli's principle is conservation of energy along a streamline. Okay, and this demo, by virtue of the fact that we lifted the paper, we know that conservation of energy is not true. We're violating that assumption that makes Bernoulli's principle valid. So right there, that should be at least a yellow flag telling us, we got to stop and think and be careful here. We learned that it's the fluid, air or water, being entrained in this jet through viscosity that creates the lower pressure between the jet and the paper. Okay, and that's what lifts up the paper, not Bernoulli, right? And in some cases, you know, if the paper is stiff, like that aluminum was, you actually even bend the flow, which is definitely not a Bernoullian behavior. Okay, it's certainly consistent with Newton's laws and Newtonian behavior, but it's not explained by Bernoulli. Okay? Bernoulli is a very narrow equation that just applies to conservation of energy along a streamline. So at this point, I hope you found that somehow useful. And again, for a science fair, you've got physical demonstrations, you've got math, you can explain Bernoulli's principle, you can show the mechanical analogy, you can explain the principle of work and energy if you want to show how pressure is a form of potential energy as it's used in Bernoulli's equation. So there's some math you can do in there to show off. And yeah, if you want to do this for a science fair, I'd encourage that, just to get facts out there instead of myths. Okay? Thanks for watching, and I'll catch you on the flip side.